Welcome to this lecture of numerical analysis. In this lecture, we will study Euler's methods for numerical solutions of initial value problems. We have actually three Euler's method. We shall call the first method as Euler's method simply. The second one is Cauchy-Euler method, and the third one is modified Cauchy-Euler. So we begin with an initial value problem. Given an initial value problem of this form, like y dash is equal to f of xy with the initial condition y of x naught is equal to y naught. We will be given this kind of a problem, and we will also be given one quantity h, which is a small real positive real number, and then we will define xn is equal to xn minus 1 plus h. Now first let's define the Euler's method and see how we can solve a given initial value problem using Euler's method, as we will define again xn as xn minus 1 plus h. So in all the three methods we have the same definition for xn. So xn is equal to xn minus 1 plus h. Then the nth iteration using the Euler's methods is given by then yn plus 1, which is defined as the nth iteration. It is defined as yn plus k1, where k1 is defined as h into f of xn yn, where f of xy is this function given in our given initial value problem. And second, we will come to the Cauchy-Euler method. Again, we have the same definition for xn, so we again define xn as xn minus 1 plus h. Then the nth approximation in Cauchy-Euler method is given by yn plus 1, which is equal to yn plus k1 plus k2 divided by 2. So we are using a new quantity k2 here. So where k1 is defined as we have defined it earlier in Euler's method. K1 is defined as h f of xn yn. And now k2 it is defined as h f of xn plus h yn plus k1. So therefore the second coordinate of k2 uses the previously calculated k1 also. And now we can come to define the formula for using modified Cauchy-Euler method. Again, we have the same definition for xn. We again define xn is equal to xn minus 1 plus h. Then the nth iteration is given by yn plus 1, which is equal to yn plus k2 only, where this k2 it is defined as h f of xn plus h by 2 yn plus k1 by 2, where this k1 is defined as we have defined it earlier. This is h f of xn yn. So therefore we can see these are the three Euler's methods, and in all the three methods we define this k1 as h f of xn yn and define the Euler's method as yn plus 1 is equal to yn plus k1, where k1 has this definition. And in the Cauchy-Euler method, we define the nth approximation using this formula yn plus 1 equal to yn plus k2 divided by 2, where k1 is as defined in the Euler's method h f of xn yn, and k2 is defined as h f of xn plus h yn plus k1. And in the modified Cauchy-Euler method, we define again xn is xn minus 1 plus h, and yn plus 1 is now defined a little bit differently. It is yn plus k2 only, where k2 is h f of xn plus h by 2 yn plus k1 by 2. But now this definition of k1 also uses definition of k2 uses k1 in its second coordinate. So we are forced to define k1 again, and k1 is defined in the same way as we have defined it in Euler's method or Cauchy-Euler method, and k1 is h f of xn yn. So these are the three methods that we are going to study in this lecture, and we will try to use them and solve a differential equation using all the three methods. So let's come to a problem. So first we shall put our problem so that we can apply these Euler's methods. So in the solution, what we are given f of xy is equal to minus 2x y square. We are given x0 is equal to 1 because y of x naught is equal defined as y naught in the definition. So we have y naught is equal to 1, and we are given that h is equal to 0.1. Now first we shall evaluate what is x1, what is x2, and what is x3 so that we can arrive at 1.3. So then we have, by definition, xn is equal to xn minus 1 plus h, and here we take n greater or equal to 1. So therefore x1 is equal to x naught plus h, and x naught is equal to 1, h is equal to 0.1, so this becomes 1.1. x2, which we now defined as x1 plus h, so it is equal to 1.1 plus 0.1, so this is equal to 1.2. And then similarly x3, this is equal to x2 plus h, so this is equal to 1.2 plus 0.1, so this is equal to 1.3. So therefore, as we are asked to find y of 1.3, so what we are actually asked by definition, we have these things. So this is our refer here. We define y of x naught is equal to y naught. That is the notation for y naught, or that is the notation for y of x naught. Similarly, we can take the notation y of x1, which is equal to y1. Similarly, y of x2, we can call that as y2, and y of x3, that we shall call as y3. But now here our x3 is equal to 1.3, so this gives actually y of 1.3, this is equal to y3. Therefore, what we are asked in the question, we are asked to find the third iteration using Euler's method, and now we will use all the three methods to find this y of 1.3. Method 1, which we call Euler's method, by definition we have this yn plus 1 is equal to yn plus k1, where this k1 is defined as h f of xn yn. So now let's compute the iterations one by one. So therefore y1 is equal, so now let's put n equal to, sorry, we have to first calculate. Okay, so this is y1 here, we will put n equal to 0 here. We will get y1 equal to y0 plus k1. Now y0 is equal to 1, so this is equal to 1 plus k1. But now we will evaluate what is our k1. So now k1, by our definition, this is equal to h f of x0 y0, because we have to put n equal to 0 here in the definition of k1 also. So this is equal to h, now f of x0 y0, that is minus 2 x0 into y0 square. Now let's substitute the values for all the variables. H is equal to 0.1, then multiply minus 2, multiply x0, that is 1, multiply 1 square, so this finally becomes 0.2, in fact minus 0.2. So 2 into 0.1 is 0.2. So therefore, hence from equation 1, we obtain y1 is equal to 1 plus k1, which is now 1 minus 0.2. So this is equal to 0.8. So that is our first iteration. Now moving towards defining the second iteration. So next, in order to obtain the second iteration from this formula, we put n equal to 1. So we will get y2 is equal to y1 plus k1, where k1 is equal, again put n equal to 1 here. So we get k1 as hf of x1 y1. So therefore we need to note here that k1 is not same in all the iterations. In y1, k1 was defined as h f of x0 y0, because y1 was obtained by putting n equal to 0 here. So when we put n equal to 0 in k1, we obtain f of x0 y0. Now for y2, we will put n equal to 1 here, we get y2 as y1 plus k1. And in k1, when we put n equal to 1, we get h f of x1 y1. So now let's call this as equation number 2. Now first let's calculate k1 here. So now our k1 here is equal to h f of x1 y1, which now by definition of f of xy, this is equal to h into minus 2 x1 y1 square. Now substituting the values of the variables, h is 0.1, then minus 2, then x1, as we have calculated x1 earlier, x1 is equal to 1.1. So x1 is equal to 1.1, and y1 obtained above, that's equal to 0.8. So this is equal to 0.8 whole square. Now using the calculator, multiplying these all variables, we get k1 here is minus 0.1408. So therefore, thus our y2, which is now defined as y1 plus k1. Now y1 is equal to 0.8. Now k1 is minus 0.1408. Now adding these two variables, we get 0.6592. So that is our second iteration. Now that our third iteration similarly becomes next y3 is equal to y2 plus k1. So let's call this as equation number 3, where now k1, that will be equal to h f of x2 y2, which is equal to h into minus 2 x2 y2 square. Now using the values, so this is equal to 0.1 into minus 2 into value of x2, which was earlier calculated as 1.2, and y2 is calculated in the previous step, that is 0.6592 whole square. Now multiplying these numbers, we get the value of k1 as minus 0.141042. So that is the value for k1, which we shall now use in equation 3 to obtain the value of y3. Hence y3, which is equal to y2 plus k1, and our y2 is equal to 0.6592 plus k1, that is minus 0.1042. Now adding these two numbers, we get 0.5549. 0.5549. And as earlier discussed here, y3 was actually y of 1.3. So therefore, hence y of 1.3, this is equal to 0.5549. So that is our value of y of 1.3 using the Euler's method. Now we shall come to apply the Cauchy-Euler method for the same formula. So our method 2 is Cauchy-Euler method, and here we have, by definition of Cauchy-Euler method, by definition, this yn plus 1. Now this is defined as yn plus 1 by 2 into k1 plus k2, where k1 is defined as h f of xn yn, and k2 is defined as h f of xn plus h yn plus k1. Now let's evaluate the iterations one by one. So therefore, thus the first iteration y1, which will be obtained from the general formula by putting n equal to 0. So we get y1 is equal to y0 plus k1 plus k2 divided by 2. So let's call this as equation number 1 again, where k1 is equal to h f of x0 y0. But since this has the same definition as we did it in Euler's method, so this will have the same value, minus 0.2. Okay, and now k2. Now this is equal to h f of x0 plus h y0 plus k1. So this is equal to h f of, now x0 is 1, h is equal to 0.1, y0 is 1, and k1 is minus 0.2. So this is equal to h f of 1.1 comma 0.8. Now using the definition of f of xy and the variable h, so this is 0.1 into minus 2 into 1.1 into 0.8 whole square, and now this becomes equal to, okay, this is the value for k2 here. Therefore we have obtained the value of k1 and k2, since so therefore hence we can evaluate this y1 now. So therefore y1 is equal, from equation number 1, it is equal to y0, that is 1, plus k1, that is minus 0.2, k2, that is minus 0.1408 whole divided by 2. Now adding these numbers, we arrive at the conclusion 0.8296. So this is equal to 0.8296. So that is our first iteration using Cauchy-Euler method. Now similarly the second iteration is, so next, now y2, that is equal to y1 plus k1 plus k2 divided by 2. Let's call this as equation number 2, where now k1, that's equal to h f of x1 y1. Now this will have the same value, now this will be changed. So this is equal to h into minus 2 x1 y1 square. So therefore this is equal to, now h is equal to 0.1 into minus 2. Now x1 is 1.1 and y1 that's equal to 0.8296 whole square. So therefore in our y2 the value for k1 is 0.1514, that is equal to minus 0.1514. That is the value for k1. And second, k2, which by definition is equal to h f of x1 plus h y1 plus k1 now. So this is equal to h f of now x1 plus h, x1 is equal to 1.1 and h is 0.1, so this becomes 1.2, and y1 is equal to 0.8296 and k1 that's equal to minus 0.1514. Then we can also write this as this becomes equal to minus 0.1103. This is 0.1103. So that is the value for k2. Hence we can obtain the value for hence from second. Hence from equation second we obtain the value for y2, which is equal to y1 plus k1 plus k2 divided by 2. Now substituting the values we get this is equal to, now adding these all we get 0.6987. So that is the second iteration y2. So finally we can arrive at the third iteration y3. Now finally next similarly y3 is equal to y2 plus k1 plus k2 divided by 2. Let's call this as equation third, where now k1 this is equal to h f of x2 y2, that is equal to h into minus 2 x2 y2 square. So that is 0.1 into minus 2 into x2, that is 1.2, into y2, that is 0.6987 whole square. Next, similarly k2 this is equal to h f of x2 plus h y2 plus k1. Okay, so this is equal to minus 0.1171. Now using this value here we get h into f of, now this is 1.3, now y2 plus k1 815, now this is equal to 0.1 into minus 2 into 1.3 into 0.5815 whole square. Okay, now this finally becomes minus 0.0879. So therefore we can finally arrive finding the value of y3. So hence y3 it is equal to y2 plus k1 plus k2 divided by 2, and the value for our y2 is 0.6987. Value for k1 this is 0.1171. Now 0.0879 whole divided by 2. Now finally this becomes equal to, so this is 0.5961. So that is how we use Euler's method or the Cauchy-Euler method for solving the initial value problems. Now we shall move further and solve the same question using the modified Cauchy-Euler method. So this now we have the method number 3, modified Cauchy-Euler method. And again here we by definition we have this yn plus 1 is equal to yn plus k2, where we have this k2 is equal to h f of xn plus h by 2 yn plus k1 by 2, and k1 is defined as earlier f of xn and yn. So therefore the first iteration yn is equal to y1 is equal to y0 plus k2. Let's call this equation number 1, where now first we again calculate k1. Now k1 is equal to h f of x0 y0, and this will be as calculated earlier minus 0.2. And second k2 which is equal to h f of x0 plus h by 2 y0 plus k1 by 2. So this is equal to h f of, now x0 is equal to 1 plus 0.1 divided by 2, y naught minus 0.2 divided by 2. So this becomes h f of is 1.05 comma 0.9. Now by definition this is equal to 0.1 into minus 2 into 1.05 into 0.9 whole square. Now this finally becomes minus 0.1701. So that is our value for k2. Therefore our first iteration y1, that is equal to y naught plus k2. Now y naught is 1, k2 is minus 0.1701. This finally becomes 0.8299. 0.829. So that is our first iteration using the modified Cauchy-Euler method. Now similarly moving further, so next y2, that is equal to y1 plus k2. Let's call this equation number 2, where now k1 is equal to h f of x1 y1, that is equal to 0.1 into minus 2 into x1, that is 1.1 into y1, that is 0.8299 whole square. Now using this, multiplying all these numbers, we get 0.1515. And second, k2, by definition this is h of x1 plus h by 2 y1 plus k1 by 2. So this is equal to h f of x1 is equal to 1.1 plus 0.1 divided by 2. Now here we have 0.8299 minus 0.1515 divided by 2. This is the value for k1 by 2. So now this is equal to h f of 1.15. Now second number is 0.7541, and finally this is equal to 0.1 into minus 2 into 1.15 into 0.7541 whole square. And now multiplying all these numbers, we get minus 0.1308. Hence our k2. So we have calculated the value of k1 and k2. Hence y2 is equal to y1 plus k2. Now y1 is equal to 0.8299 minus 0.1308. Now adding these numbers, we get 0.699. Now coming to the next step, the final iteration y3, which we now call y2 plus k2, which we call equation number 3, where again now k1 is defined as h f of x2 y2, and k2 is defined as h f of x2 plus h by 2 y2 plus k1 by 2. Now we will leave the remaining part of this question as an exercise to evaluate this. What is the value of k1 using x2 is equal to 1.2 and y2 is 0.699. Then you will get the value of k1. Now using this key value of k1 here and x2 as 1.2 here, h as 0.2 here, you will get the value of k2. Then using this value of y2 as 0.699, then value of k2 obtained from here to get the value of y3. So remaining part is left as an exercise. And for more practice purpose, we will also keep one more question here. So this will be the question for practice. Thank you so much.